So now we can introduce the adjoint or the adjugate matrix. So the adjugate matrix is simply the transpose of the cofactor matrix. We can find the inverse of a matrix A by taking the product of the adjugate matrix with the inverse of the determinant. So similarly, the solution to AX equals B can be found by multiplying the adjugate matrix times B and dividing by the determinant. Now, Cramer's rule. We can take some system AX equals B. So we're going to find D. D is the determinant of A. We're then going to find D sub X. D sub X is the determinant of A sub X. And D sub Y, where D sub Y is the determinant of A sub Y. We're going to replace the first column with B. A sub Y, we're going to replace the second column with B. So, finding the determinant of each of these, we're going to have 1 times minus 1, which is minus 1, minus 1 times 1, which is minus 2, over here. We're then going to find the determinant of this here, 4 times minus 1, minus 1 times 0 is going to be minus 4, just D sub X. And finally, we're going to find the determinant of A sub Y, which is going to be given by the determinant of this here, which is minus 4, as here. x1, x2, the vector, is going to be given by D sub X divided by D, and D sub Y divided by D. That gives us this over here. x1, x2 is going to be minus 4 divided by minus 2 for x, and minus 4 divided by minus 2 for y. So we're going to get the matrix 2, 2. As you can see above, this solves it in the exact same way as the example we covered before. Of course, this does work for 3x3 matrices and larger, but is very, very time consuming, so you may well be better off performing Gauss-Jordan elimination. So quickly, some definitions you might need. So a set of vectors will span the space if any combination of those vectors can produce any vector you can possibly think of within the space. So, for example, the XYZ coordinate system works so well because you can take any component of this vector, any component of this vector, and any component of this vector and produce any vector within the XYZ space. So those vectors span the space. Vectors are linearly independent if you can't multiply one by some scalar to get the other. A set of vectors will span the space if they are linearly independent and the number of vectors is the same as the number of dimensions of the space. For example, you can't have 3 vectors span a 2-dimensional space. A subspace, a similar idea to that of subsets in junior cert maths. A smaller space can be made from one of higher dimensions. So for example, you can have a 2D plane in a 3D space. You can have 3D Euclidean space in 4D spacetime. These are subspaces, but don't forget that a subspace must contain the 0 vector in order for it to be a subspace. Lastly, a basis is a set of vectors that span a space. It's used to describe the other vectors in the space. So for example, the XYZ coordinates are used to describe a basis of 3-dimensional space. So really quickly, the parameterization of a matrix. So if we take the example we did before, we have a reduced row echelon form of some matrix that we covered earlier, 1, 2, 0, 0, 0, 1. If we consider the equation AX equals 0, this gives us x1 plus 2 times x2 plus 0 times x3 equals 0, and x3 equals 0 over here. Right, so let's say we set a free variable here. The only free variable we have is x2. We're going to let x2 equals s. Then, rearranging this here, this guy here, we're going to have x1 equals minus 2 x2 equals minus 2 s, since we've let x2 be s. So now, we can rearrange the vector x1, x2, x3 in terms of s. We can write that as x1, x2, x3 is minus 2s, x2 we defined as s, and x3 we know is 0. So now we have a vector completely in terms of s, so we can write x1, x2, x3 as the vector s times minus 2, 1, 0. Here's a particular example that's much, much larger. So we're letting all these here, along this diagonal here, are all pivots. Everything inside the pivots on this side of the dotted line are free variables. So using AX equals 0, we're going to let x5, x6, and x7 equal to SVT. We've got 3 variables. The dimension of the matrix is 3, so we can say the dim of A is 3. Now, using this set of linear equations, we're going to have these equations here. and so on. So say, for example, from the first row here, we have x1 plus 7 times s, that's x5, plus 1 times v, this is x6, plus 3 times t, which is x7, equals 0, and so on. Now, having let x5 equal s, x6 equal v, and x7 equal t, we're going to rearrange each of these in terms of s, v, t. This is what we get here. So we let x1 equal all of these on the opposite side, we get this. x2 equals all of these on the opposite side, we get this, and so on. Now, we can separate these out into vectors in s, v, and t. In doing so, we're going to have, say, for example, minus 7s, 17 over 3, s, minus 2s, minus 16s, 1s, and then 0, 0. That's what we get here. Same here, we've got minus v, so minus 1, plus 11 over 3v, 11 over 3v here, minus v here, and so on. So, the vectors of s, v, t above here are now linearly independent. If you have a look, you can't multiply any of these vectors by any possible scalar to get one of the others. They're linearly independent.